In this video, I'm going to show you how to differentiate exponential functions using the chain rule, product rule, and quotient rule. So here we're given that f of x is x squared times 5 to the x, and we want to compute the derivative f prime of x. And here we've got a table of some rules that we can use to do this. We've got derivatives of exponential functions here. Okay, so let's get on with computing this particular derivative. This is a product, so we're going to use the product rule here. And we'll take u will be x squared, so x squared, and then v will be 5 to the x. So v is 5 to the x. And let's just run that through our product rule and go ahead and compute. So that'll be u prime, so x squared prime times v is just 5 to the x, and then plus x squared u, then times v prime, so times derivative of 5 to the x. Alright, now let's take the derivatives and compute. So derivative of x squared, we know using the power rule, that is just 2x. So first term is just 2x times 5 to the x, and then the next term, we've got plus x squared, then this time we're taking the derivative of 5 to the x. So using our table here, 5 to the x, that matches up with a to the x. We know that the derivative of a to the x is just a to the x ln a, so derivative of 5 to the x is just 5 to the x ln 5. Okay, great, so we're pretty much there. Let's just clean this up a bit. Let's factor the final result. Factoring is always a good idea because it allows us to compute interesting things about the function much easier, like stationary points, for example. So let's go ahead and look for some common terms. We see 5 to the x, that's in both the terms, so let's factor that out. So this is 2 to the x plus x squared ln 5 times 5 to the x. We can even factor out an x from both terms also. So just 2 plus x ln 5 times x times 5 to the x. And there we go. That's about as simple as we'll get it. So here it is. Here is our derivative. Alright, here's another example. Pretty similar. We're given this function. F of x is 2 to the x plus 3 over 1 plus e to the negative 4x, and we want to compute the derivative f prime of x. And we've got our table of rules for derivatives of exponential functions. This time it's a quotient though, so we're going to end up using the quotient rule. So here's the template for the quotient rule, and let's go ahead and fill that in by matching u and v with our actual function. So let's go ahead and do that. So first of all, u. What is u? Well, u is the numerator here, so u is just 2 to the x plus 3. And then how about v? v is just the denominator. v is 1 plus e to the negative 4x. So quotient rule says that we can compute this derivative by just taking u prime, so 2 to the x plus 3 prime, then times v, so times 1 plus e to the negative 4x, and then subtracting u, which is just 2 to the x plus 3 times v prime. So times the derivative of 1 plus e to the negative 4x, and that's all over v squared, so all over the denominator, 1 plus e to the negative 4x squared. And now it's just up to us to go ahead and compute this derivative. So let's go ahead and compute 2 to the x plus 3 prime. That matches the template a to the px plus q, and the derivative of that is just pa to the px plus q, natural log a. So p here, what is p in this case? Well, p is just the coefficient on the x, which is just 1. So 1 times a to the px plus q, that's just the original expression, 2 to the x plus 3, then times the natural log of a. Well, a is just the base of 2 here. So times natural log 2. Okay, so that then times 1 plus e to the negative 4x, and then minus 2 to the x plus 3 times derivative of 1 plus e to the negative 4x. Okay, so let's go ahead and compute that. Let's break the derivative up over the sum. The derivative of the constant 1 is just 0, so we can forget about that. We just care about the derivative of this term here, e to the negative 4x, and that matches this template here, e to the px plus q. That derivative is p e to the px plus q. So again, the coefficient on the x here hops out in front, negative 4, and then we've got our original expression, e to the px plus q, in this case just e to the negative 4x, and that's it for that derivative. And now let's go ahead and write our denominator. So denominator is again just 1 plus e to the negative 4x squared. Okay, cool. So now we just have to simplify this result, make it nice and clean. So let's see, can we pull out anything from the numerator here? Anything from both terms? Look, there's a 2x plus 3 in both terms, so why don't we pull that out? So let's go ahead and write our fraction bar. We'll pull that 2 to the x plus 3 out from the numerator, so write that on the outside, to the x plus 3, and what's left on the inside? Well, there's 1 times natural log of 2 times 1 plus e to the negative 4x, so just really 1 plus e to the negative 4x natural log of 2, and then what's left here? So minus a negative 4e to the negative 4x, so those negatives will cancel, become plus, because there are 2 of them, so just plus 4e to the negative 4x. That's all over 1 plus e to the negative 4x squared, and there we go. That looks about as simple as we can get it. So there is our result. That's our derivative. Alright, another example. Now we're given this function f of x is 3 to the x to the 4th minus x squared plus 2x plus 1, and we want to compute f prime of x. So for this here, we're going to introduce another rule. This rule is given by the derivative of a to the power of some function g of x. That derivative is given by the original expression a to the g of x, and then there's a bit more, so times g prime of x, and then times natural log of a. This really just comes from the chain rule, but don't worry too much about it now. We'll go over it in the next slide, but right now we just want to go ahead and apply this rule to the problem at hand. So the problem at hand, that takes the form a to the g of x, where a is 3, and then g of x is that polynomial exponent. So x to the 4th minus x squared plus 2x plus 1. And we want to take that derivative, so just match it up with the template for our rule. So that comes out to, first of all, just the expression itself, 3 to that polynomial x to the 4th minus x squared plus 2x plus 1, then times the derivative of that exponent, so times the derivative of x to the 4th minus x squared plus 2x plus 1, and then times natural log of the base. Here the base is 3, so natural log of 3. So let's just go ahead and simplify that. So again, we just have 3 to that exponent, x to the 4th minus x squared plus 2x plus 1, and then times the derivative of that exponent. So derivative, all we have to do is apply the power rule here. So x to the 4th, that becomes 4x to the 3rd, then minus 2x, then plus 2, and the constant goes away because constant derivative of that is just 0. And then at the very end, we've got a natural log of 3. And let's go ahead and factor this as much as we can, simplify it as much as we can. All that really jumps out is that these terms are all even coefficients, so we can factor out a 2. So let's factor out a 2 in front. 2 times that whole expression, 3 to the x to the 4th minus x squared plus 2x plus 1, and then times all of these coefficients divided by 2, so just 2x cubed minus x plus 1, and then times natural log of 3, and that's about as simple as we'll get it. So there we go. There is our final result. Alright, so now let's look back to that formula we used in the previous example. Derivative of a to the g of x is equal to a to the g of x, g prime of x, natural log of a. And let's derive this formula using the chain rule. So let's work it out explicitly where this formula comes from. First of all, so chain rule has to do with some function f of another function g of x. So let's decide what is our outermost function f here. So f is what is happening to g of x here. What is happening to g of x? Well, it's being raised to a power. It's being raised a to the power of g of x. So that's telling us that we should set f of x equal to that thing of raising the power a to the x. So a to the x, and then that way when we plug in g for x, then we just get a to the g of x. There we go. Okay, so why don't we go ahead and write in what we have. So here we've got plugging in that f is a to the x, then f of g of x is just a to the g of x, and that's what we want, and we're taking the derivative of that. So according to the chain rule here, that's f prime of g of x. That's the first bit of it. So let's go ahead and compute f prime. What's f prime of x? If f is a to the x, well, that's just right here in our table of rules. So that's just a to the x natural log of a. So now we're just going to have to plug in g of x into that x here to get that first term in the product. So let's write that. So a to the g of x, and then natural log of a. Okay, and then just times g prime of x, and we'll just keep that as is. So times g prime of x, and then all we have to do to get there is swap these two terms in the product. It's pretty straightforward. So now we just write it out once more, a to the g of x, then times g prime of x, then times natural log of a. And we're done. There we go. That's how we derive it. Great, so now we know how to differentiate complicated exponential functions using our derivative rules. In the future, we'll learn how to use those derivative rules to differentiate complicated logarithmic functions as well.